On the previous lecture, we were on the separation result. We were trying to separate out a particular point that is outside of a convex set, and we have found that if a point is outside a closed convex set, there is a separating hyperplane. Now we shall go for applying this particular result today in identifying certain theorems. Those are called as theorems of alternatives. On the last lecture, if we look back our class note, then we shall see that we were trying to discuss about convexity preserving operations. In the convexity preserving operations, we have given the Minkowski sum of a pair of convex sets is convex. The difference between a pair of convex sets is also convex. The Cartesian product of a pair of convex set is convex. Then next we have discussed two operations. One is the affine image and inverse affine image. We have seen that for a given convex set capital X, the affine image Fs is a convex set, as well the inverse affine image of a given convex set is also convex. We have also given two numerical examples. Those are depending on the pull back and push forward by affine function of a given convex set. Then later on we were trying to discuss about the closest point theorem or the projection operator. In the closest point theorem or the projection theorem, we have seen that if a set capital S is given to be closed, non-empty and convex set, and if there is an element y outside the set S, then there is a hyperplane that separates out the element y and the set S, and eventually the separating hyperplane is a plane that we can take in particular as the common tangent of the level set of the circles. Norm of y minus x is equal to alpha, and as well the tangent to the boundary of the given set capital S. By taking the common tangent, we can separate out the element y and the given non-empty closed convex set that we have seen. In today's class, with the help of the separation of a point and a convex set that we have derived on the last day, the last corollary, with the help of the last corollary, we will discuss today a few theorems of alternatives. A theorem of alternatives is a theorem that states that exactly one of two systems has a solution. In a theorem of alternatives, exactly two systems will be given, system 1 and system 2. Both the systems will involve inequality and equality relationships, and we shall see that exactly one of the system will have a solution, not both. So this is the theorems of alternative, and that we shall discuss about in this class rigorously. With the help of the last day's corollary, at first we shall start with the Farkas lemma, that is also a theorem of alternatives. With the help of the Farkas lemma, we will derive a few corollaries, and out of them one is the Gordon's theorem. So in today's class, at first we will discuss about Farkas lemma, then Gordon's theorem, then a few corollaries, in between some examples of the theorems of alternatives will be given, and if time permits, then we shall get into a new topic, that is the discussion on convex function. So let's start our class. The Farkas lemma states the following. It states that if we have a set of elements that constitute the system 1, those are given by a matrix inequality, let A be a matrix of order, real matrix obviously, order m by n, and C be a vector in the n-dimensional Euclidean space. Then exactly one of the following two systems to systems has a solution, but not both, exactly one. The system 1 is given by Ax less than equals to 0 and C transpose X is greater than 0 for some X belonging to Rn. Note that system 1 states that there exists one X that satisfies both the inequalities Ax less than equals to 0 as well as C transpose X greater than 0. It is not that for all X belonging to Rn, there exists one X such that both the inequalities are satisfied. The system 2 is A transpose Y is equal to C and Y greater than equals to 0 for some Y belonging to Rn. That is, there exists one Y such that this equality A transpose Y is equal to C and Y greater than equals to 0 is satisfied. Fine. Let us now try to prove this result with the help of the last day's corollary. On the last day, the corollary that we derive, with the help of that, let us now try to prove this result. This result is very important, as this result is very important in our course, because with the help of this result we will try to derive optimality conditions in nonlinear programming problems, and therefore this result is truly important. Quite often we shall use this result. Let me speak a few words about the derivation of this lemma. This result is named after the mathematician Farkas. The full name is Julius Farkas. He was one Hungarian mathematician, and this result was derived in 1902. Fine. And the result that we shall discuss as a corollary, that is the Gordon's theorem. Surprisingly, Gordon's theorem is derived much earlier than Farkas theorem. But with the help of the Farkas theorem, Gordon's theorem can be easily proved. And therefore, in this course, we will prove Gordon's theorem, another theorem of alternatives, as a corollary of the Farkas one. Anyway, and Farkas lemma obviously is then certificate of feasibility of a set of linear inequalities, because you note that the system one says that it is a system of inequalities, system of linear inequalities. If system 1 has a solution, then fine. If the system does not have a solution, then system 2 must have a solution. So you can check in either way. In order to check that whether the system 1 is having a solution, either you try to solve the set of linear inequalities. You note that solving a system of linear inequalities is not an easy fact. If we have two or three inequalities, you can check geometrically whether this set of inequality in system 1 is having a solution. However, if you have more than 5 variables and the matrix A is of order, let's suppose 6 by 5, it is not an easy task to check whether this system of inequalities is having a solution. Rather, the system 2 is easy to check, because system 2 involves solution of A transpose Y equals to C. This is a system of linear equalities. Linear equalities, feasibility of linear inequalities is little easier to check than feasibility of system of linear inequalities, because for feasibility of system of linear equalities, the Gordon's elimination process is there, where some row operations, elementary row operations you apply on the matrix A transpose or on the augmented matrix A transpose and C, and then you can check whether this system has a solution, and therefore it is easy to check whether system 2 has a solution. If you find that system 2 does not have a solution, if the system 2 is inconsistent, then obviously system 1 will have a solution. So vice versa way, either you can solve system 1 or you check whether system 2 has a solution. If system 2 has a solution, then you can state that system 1 does not have a solution. However, if system 1 has a solution, then system 2 will not have a solution. Fine. So in this way, and therefore it is called the theorem of alternatives. Either system 1 will have a solution or system 2 will have a solution. Fine. Anyway, so let us now try to prove this result. The proof will go in the following manner. At first, let's suppose the system 2 has a solution, and then we will prove that system 1 does not have a solution. Then later we will consider system 2 has no solution, and we will prove that system 1 must be having a solution. So at first, let us consider that the system 2 has a solution. Let us consider it has a solution, and if it has a solution, by that we mean there exists one y in Rm such that you have A transpose y is equal to C, and you have y greater than equals to 0. By y greater than equals to 0 here, by that we mean all the components of y are individually greater than equals to 0. Fine. Now here, once you have this consideration that system 2 has a solution, then you will appear with two possible cases. The first case is the following, that there exists one x in Rn. These two cases are exhaustive. Either ax less than equals to 0 has a solution, or there does not exist. You will fall into either of the two cases. There does not exist any x such that ax is less than equals to 0. This case eventually implies that the system 1 does not have a solution, and then your proof is done that system 2 has a solution, and in the second case, in the latter case, this will imply that system 1 does not have a solution. System 1 does not have a solution. However, if you fall into this case, how do you prove it? Let's suppose now, if there exists one x belonging to Rn such that ax is less than equals to 0. If this is happening, then let us now compute what is C transpose x. We note that you have assumed that there exists one y such that A transpose y is equal to C. So let us now plug this expression of C over here. Expression of C is A transpose y transpose x, and this will give us y transpose ax. Fine. Here you note that this ax is less than equals to 0, and the components of y, these are all greater than equals to 0s. Fine, because y is such that A transpose y equals to C, as well as all the components are greater than equals to 0, and therefore this gives rise C transpose x is less than equals to 0, and this implies then system 1 has no solution. Fine, and you are done. That if system 2 has a solution, then it concludes that system 1 cannot have a solution. Now next let us now prove the next possible case, where we will consider that the system 2 has no solution, and we will prove that system 1 must be having a solution. Let us now try to prove it. The another case we consider now, let system 2 has no solution. Suppose system 2 has no solution. Fine. And we have to prove then system 1 has a solution. Now if system 2 has no solution, then if we consider the following set, consider capital S set of all elements in Rn such that A transpose y is equal to V
y greater than equals to 0, and here y are elements from Rn. Fine. And therefore obviously C is not belonging to this set, is not that? Because if C is belonging to the set S, then obviously for one y you will have A transpose y is equal to C, because these are the elements of the set S, is not that? And therefore immediately we find that C is not belonging to S. You also note that the set S is non-empty, because you can take here in particular y equals to 0, and accordingly you will have V as a null vector, and that null vector is belonging to S, and therefore we note that the set S is non-empty. And also we note that the set S is convex. You can quickly prove it by the definition of convexity, and or otherwise you can check that this set S is a polyhedral set, and therefore this is a convex set. You can quickly check it as a home task. I am keeping it is as a home task. You check that this is a convex set, and not only convex set, this is also a closed set. Fine. Now you also try to prove why is it a closed set. Now I will give a hint over here. For closed set, you note that there is a result. If you take any sequence Vn inside the set S, all the elements of Vn are inside the set S, and then you prove that the limit, you consider a converging sequence, any converging sequence Vn in the set S, and then you prove that wherever it converges, that is also belonging to S. This is a characterization of a closed set, and accordingly we will prove that S is convex and it is also a closed set. And therefore this line, what does this line says? This line says that C is not in a non-empty closed convex set. Now we can apply the result on the last day. The last day we have seen that if an element is outside a closed non-empty convex set, then by the projection theorem, or the corollary to the projection theorem, by the corollary, the last day's corollary I am referring, of the projection theorem, what we shall have is a non-null vector P, there exists a non-null vector P and a scalar alpha such that P transpose C is greater than alpha and P transpose X is less than equals to alpha for all X belonging to S. Immediately from this consequence that P transpose X is less than equals to alpha, we note that obviously this will prove that alpha is non-zero, because as the null vector is belonging to S, we have P transpose the null vector is less than equals to alpha. That is, you have alpha a non-negative quantity. Fine. And if this is true, then we note that from the same inequality from the same inequality, let me name as 1. From 1, not only we have alpha greater than equals to 0, but also from 1 we have the following. We note that alpha is greater than equals to P transpose X or P transpose V. Generic elements of the set S is considered to be V. So here P transpose V for all V belonging to the set S. Fine. And these will then imply alpha greater than equals to, what are V's? V's are given by, inside the set S, V's are given by A transpose Y and Y greater than equals to 0. Fine. So here P transpose V's expression is A transpose Y. Fine. And this is true for all Y greater than equals to 0. and this will then imply, you note the interesting fact that AP transpose y is less than equals to alpha for all y greater than equals to 0. What does it say? It says that, here you note that AP, this is a AP here, this is a constant vector, and here y is a variable. Fine. Now this inequality then, AP transpose y less than equals to alpha, says what? And alpha is a non-negative quantity. Here is your real number line, here is the location of 0, and let's suppose the quantity alpha is over here. Alpha is greater than equals to 0. Here you note that AP transpose y for every y is less than equals to alpha. Now we note that this is not possible. This is not possible if AP is not less than equals to 0, because if AP is greater than 0, then what will happen? You can make the element y, you can choose arbitrarily large this y, and you multiply with positive quantity AP transpose, and obviously as y is a variable, you can make it arbitrarily larger, and therefore the entire quantity will just blow up and it will exceed at some level, at some choice of y, it will exceed alpha. In particular, let me be very precise. If AP is greater than 0, then here we claim that AP must be less than equals to 0. If AP is greater than 0, then in particular we choose, then by choosing y is equal to, let me choose 1 plus alpha, let me tactfully choose 1 plus alpha divided by norm of AP square. Norm of AP is not 0, and therefore this division is well defined, times AP. Fine. And obviously this quantity qualifies to be greater than 0, because alpha is greater than equals to 0. AP, this vector is greater than 0 you have considered here, and therefore y is an element whose all the components are greater than 0. Fine. If we take this, then by choosing this, we see that AP transpose y is equal to, obviously AP transpose y, you just calculate quickly, you will get 1 plus alpha, and this 1 plus alpha is obviously greater than alpha, and which is contradictory to the inequality 2, which is a contradictory to contradictory to 2. This is not possible, and therefore this is due to the fact that AP greater than 0 you have chosen, and therefore our claim is true that AP is less than equals to 0, and then your result is done, that AP less than equals to 0, that you have proved, and you have seen that alpha greater than equals to 0, and from 1, then from this star, let's suppose this is my star, so from star, and let's suppose this 3, and also you have alpha greater than equals to 0, so everything together, let me just be precise, P transpose C is greater than alpha, hence from P transpose C greater than alpha, alpha greater than equals to 0, and AP less than equals to 0, we see that system 1 has a solution, and therefore your result is proved, that you have checked both the cases, that at the first case you have taken that system 2 has a solution, then you have proved that system 1 does not have a solution, then later on you have proved that If system 2 has no solution, then system 1 must be having a solution. And this completes the proof of the Farkas lemma. Now, as a corollary to this result, we'll prove next the Gordon's theorem. But before getting into Gordon's theorem, let me geometrically explain the geometrical intuition behind the Farkas lemma. Let me geometrically explain. It has a very nice geometrical interpretation. Geometrical intuition. Geometrical intuition is the following for Farkas lemma. It is the following. A very nice geometrical fact is involved in the system 1 and in the system 2. Fine. Now let me explain. Now what does the system 1 says? System 1. Let me try to find what does system 1 say. System 1. System 1 says the following. System 1 is saying that there exists one x belonging to Rn such that Ax is less than equals to 0 and C transpose X is greater than 0. This is your system 1. What does this system says? Let me try to find what is the geometry behind Ax less than equals to 0. Geometry of Ax less than equals to 0. Let me vary x also and find what is Ax less than equals to 0. Now Ax less than equals to 0, here A is a matrix. A is a matrix of order m by n. Let me say the row vectors of A are the following. A1 transpose, A2 transpose, and it has m many rows, so you have AM transpose as the end vector. Here each and every AI is an n-dimensional column vector. Fine. And this will constitute then the matrix A. A is of order m by n. Fine. Now if we in particular choose 2 to 3 elements, let's suppose A involves 3 vectors. Those are let's suppose here is your origin, and then A1 vector is this vector. A1 is this. Then what is the meaning of A1 transpose X less than equals to 0? It is nothing but the left side of the hyperplane A1 X is equals to 0. This is the hyperplane. This is the hyperplane, that is your A1 transpose X is equal to 0. And its perpendicular is the vector A1. Fine. And obviously you note that the A1 transpose X less than equals to 0 is the different side than the side of A1, because here if you plug X equals to A1, then A1 transpose into A will give us a positive quantity if A1 is a non-null vector, obviously. So here is, if this is the direction of A1, here is your origin, then this side locates your A1 transpose less than equal to 0. Fine. Now if we have two vectors, another vector, let's suppose another vector A2, let me draw with a different color. If A2 is my, let's suppose A2 is my this direction, A2 is my this direction, A2. Fine. Then accordingly A2x, obviously A2x equal to 0 will be perpendicular to A2. Fine. And therefore this is the region, this red shaded region is the region for A2x. This region is for A2 transpose X less than equals to 0. Fine. Now if you have another vector A3, say A3 is over here, then you will find that, let's suppose this is your A3, then A3x perpendicular to A3x equals to 0 is this one, and then this shaded region will give us, this green shaded region will give us, this region is your A3 transpose X less than equals to 0. Then accumulately we note that if we consider these three inequalities, A1 transpose less than equals to 0, A2 transpose less than equals to 0, and A3x transpose less than equals to 0, then this region, this and this is the boundary, fine. Then this region gives us Ax less than equals to 0. Fine, this black shaded region will give us Ax less than equals to 0, where A is the three vectors that I have considered: A1 transpose, A2 transpose, and A3 transpose. Fine. And if we have m vectors, you can equally find by increasing number of components A1, A2, A3, you will find what is the inequality for Ax less than equals to 0. This is the shaded region, Ax less than equals to 0. Now, this is the geometry of Ax less than equal to 0. And for the geometry of C transpose x greater than 0 is similar. For C transpose x greater than 0, what you will have is the following, that you have a C vector C, and C transpose x is strictly greater than 0, and therefore the boundary of C transpose x will not be considered. Let me suppose origin is over here, and this is my vector C, and C transpose x greater than equals to 0 is this region. Fine, is this region. Now system 1 then geometrically signifies that this region C transpose x and this black region Ax less than equals to 0 has an intersection, or otherwise system 2 is having a solution. Now here we note that with this geometrical fact, the geometry that I have explained for Ax less than equal to 0 and C transpose x greater than 0, we note the following, that you have two possible cases. The first case, the case 1 says that you have the vectors A1, you have the vector A2 say here, you have the vector A3 say here, you have another vector, let's say A4 is here, fine. And you can have two possible cases, that C is lying inside this cone in between A1 to A4. The cone generated by these four vectors A1, A2, A3 and A4 is this dotted region. And you note that you have two possible cases. Either C is belonging to this cone, let's suppose C is over here, or otherwise another case is the following. Case 2 is C is outside this cone generated by A1 to A4. Or let's suppose here is your A1, then here is your A4, then here is your A2, here is your A2, and here is your A3, here is your A3, fine. And this is the cone generated by the vectors A1, A2, A3 and A4. Now either you will have C inside this cone, or C will be outside the cone, anywhere outside this dotted region. If C is inside the cone, then what will happen? You note that if C is inside the cone, then you can find a positive linear combination, that non-negative quantities y1, y2, y3 and y4, all of them non-negative, all of them are greater than or equals to 0, such that C is equal to y1 a1 plus y2 a2 plus y3 a3 plus y4 a4. This is very simple to construct. How? We know that if C is this direction, then we can eventually draw a parallelogram in the following manner, that you can draw a line parallel to A3 from C. If we try to draw, then this is parallel to A3, and here you also construct a line parallel to A1. So if this is the vector, let's suppose this green vector is your y1, a non-negative times a1, because this is parallel to a1, and this green vector is, let's suppose, your this green vector is y3 a3. Obviously y1 and y3, they are non-zeros and they are positive quantity eventually, as this is the diagonal of this parallelogram, and therefore C can be observed as y1 a1 plus y3 a3, where y1 and y3, they are non-zero quantity and also they are positive quantity. And you consider this the component y2 with a2 equals to 0, you consider this y2 is equal to 0, and also consider y4 equals to 0, then you can find that C is obviously a non-negative linear combination. There exist non-negative values y1, y2, y3, y4 such that C is this linear combination y1 a1 plus y2 a2 plus y3 a3 plus y4 a4. Wherever C you consider, you could have considered C over here. Then accordingly, with the help of a2 a4, you will find what is this combination, that y1 a1 plus y2 a2 plus y3 a3 plus y4 a4. What is this combination to construct the value of C? And this implies what? C equals to, this implies this is nothing but A transpose Y. So it says that there exists one Y. Now construct with this y1, y2, y4. You construct the vector Y with these components y1, y2 till y4 such that A transpose Y is equal to C. And the case 1 is eventually then the geometry of system 2. Fine. Case 1 is nothing but your system 2 is having a solution. For case 2, we note that once you have C outside the cone, then we note that Ax less than equal to 0 for this figure is having the following geometry. You consider perpendicular to the last vector A4. Fine, this is the region for capital Ax less than equals to 0. This region Ax is less than equals to 0. And once your C is outside the cone, and therefore if we try to draw what is your C transpose X is equal to 0, then you find that C transpose X is equal to 0 is this dotted red line that is perpendicular to C, and then C transpose X greater than 0 is obviously this red shaded region, and here we note that this red shaded region and the black shaded region gives you a non-empty intersection, and therefore there exists at least one x. You consider any x inside this region, in this red region, in this region you consider, in this region, from this region you consider any x, and that x will satisfy both C transpose X greater than 0 as well you have Ax less than equals to 0, and therefore case 2 is nothing but system 1 is having a solution. The geometry of system 1 has a solution, fine. And this simple geometry says that obvious that system, either system 1 will have a solution or system 2 will have a solution, because either C will be inside the cone in between A1 to A4, or C will be outside the cone in between A1 to A4, and therefore geometrically it is very clear that either system 1 will have a solution or system 2 will have a solution, fine. Anyway, so we will not prolong much this discussion. Now let me go ahead next as a corollary to this Farkas lemma. The corollary is the Gordon's lemma or Gordon's theorem. Corollary 1. Corollary 1. It is your Gordon's theorem. Gordon's theorem. It states the following. Gordon's theorem, as I have mentioned, it was discovered much before than Farkas lemma. Without the help of Farkas lemma, Gordon has derived in 1873, and it was published in the Journal of Mathematics KANPUR-NPTEL in the volume number 6, and in page 23 to 28 you will be able to find this Gordon's theorem. And this Gordon's theorem was proved without the help of Farkas lemma originally. However, after the derivation of Farkas lemma, Gordon's theorem, the proof of the Gordon's theorem became easier, and that easy proof I will mention here. The statement of the Gordon's theorem is the following. It says that let you have a matrix, let A be an m by n matrix. You have one m by n matrix, fine. Then exactly, obviously real matrix we are considering. The entries of A's are real. Then exactly one of the following systems has a solution, not both. As a solution, not both. The systems are the following. System 1. The system 1 is Ax is strictly less than 0 for some x belonging to Rn. That is, there exists one x such that Ax is less than 0, and the system 2 is A transpose y is equal to 0 for some non-null y, for some y that is not null but greater than equals to 0, fine. And here y is an element in Rm, fine. These are the statement. Now let us try to prove this result with the help of the Farkas lemma. The proof is the following. We note that the system 1 can be written. Let us try to write the system 1. Let us try to write the system 1 similar to the system 1 in the Farkas theorem. The system 1 is equivalent to that. Here you note that Ax less than 0. So here by adding slack variables you can find that there exists one s such that Es plus Ax is here less than equal to 0 for some x in Rn, and s is a slack variable must be greater than 0, fine. Now can you clearly find why this is so? How can you find this y? Now as a homework I am keeping it. Can you be very precise how to find this s? Fine. Here you note that a has m many components. This ax less than equals to 0, this ax less than equals to 0 is eventually having m many components. Is not that a1 transpose x less than 0, a2 transpose x less than 0, then a3 transpose x less than 0, then till am transpose x less than 0, fine. And from there to each and every inequality you keep on adding s1 s2 s3 until sm, and you define this s as the minimum most of s1 s2 till sm, and you will find that the system 1 is equivalent to ax plus es is less than equal to 0, fine. Where e, by e I must mention, where e is an m dimensional vector, all the m tuples has ones, fine. M many ones, fine. And by es, then es is nothing but s, all the components are ss. Now to be more equivalent, by that I mean to be more exact with the system 1 of Farkas theorem, let me try to write what is the precise a in the Farkas theorem. we note that we can write this inequality by A E and X S. Fine. That means you are adding one more column E, and this is less than equals to 0 for some x belonging to Rn and S is a scalar greater than 0. Fine. This is your system 1. And then obviously this is your the matrix A in the Farkas lemma, and the variable is obviously having n plus 1 components x together with S. Fine. Now the corresponding system 2 in Farkas lemma is the following. We must write this s greater than 0 equivalent to C transpose x greater than 0. What would be corresponding C here then? We take C as all zeros, 0, 0, 0 till 0. Here you have n many zeros, and the last component you take 1. Transpose of it is equals to C, and then you take x is the vector together with S. Then it will give us C transpose x greater than 0. Fine, this is your C, and this is your system 1. The corresponding system 2 in the Farkas lemma is A transpose y is equal to C for some y greater than equals to 0 and y belonging to Rm. That is your system 2 in Farkas lemma, right? Let us try to write the equivalent system. Here we note that this is equivalent to A transpose y is equal to 0 and E transpose y is equal to 1 for some y greater than equals to 0, y belonging to Rm, right? And this is equivalent to then A transpose y is equal to 0 and E transpose y, this will give you y1 plus y2 plus till ym is equal to 1 and y greater than equals to 0 for some y in Rm. Now we note that this condition, that their addition of the components is equal to 1 and all the components of y are greater than 0, eventually says that this is equivalent to y greater than equals to 0 and y cannot be a null vector. Fine, y belonging to Rn. This is precisely the system 2 in the theorem, and therefore from Farkas lemma we have then proved that either Ax less than 0 is having a solution, or the system 2 A transpose y equals to 0 for some y is having a solution. Fine, this proves the result from Farkas lemma, right? Now next we shall try to prove another two corollaries. Those are immediate from the Farkas lemma. Corollary 2, it states that let A be a matrix of order m by n. Let A be a matrix of order m by n, be a matrix, and C belonging to Rn. Fine. Then exactly one of the system has a solution. What are those systems? System 1 is Ax is less than equals to 0, x is greater than 0, C transpose x is greater than 0 for some x belonging to Rn, and the system 2 is A transpose y is greater than equals to C, y greater than equals to 0 for some y belonging to Rm. Fine. And as a proof, let me just hint out the proof. Again, you try to write the system 2 as equivalent to the system 2 in the Farkas lemma. System 2, we know that is equivalent to, you can write it as, with the help of a surplus variable, you can write A transpose y minus identity matrix into S. Here this S is not a scalar S, this S is a vector S and is equals to C. Here S is having S1 for the first component, S2 second, until Sn. In many components you have is equals to C. Together with this you have Y and S, these two vectors Y and S. Consider to write in this way, and these are greater than equals to 0 for some Ys. For some Ys is belonging to R, Y is in Rm and S is in Rn. Fine. And this is sufficient hint. Now this can be written as A transpose minus the identity matrix of order n. In you can write here in, and then you consider y, the vector s is greater than equals to 0 for some ys belonging to R m plus n. Fine. And sorry, I'm very sorry here, this is equal to C, not C. This is not 0, this is C. Fine. And therefore you now write it as A transpose y is equal to C with y greater than equals to 0. That is your system 2 in Farkas lemma. Now find the corresponding system 1. This is sufficient hint. And I also, let me mention the another important result. With the help of that result, we will try to prove the KKT's theorem. The next corollary, corollary 3 to the Farkas lemma. Corollary 3 is the following. It states that let A be a matrix of order m by n and B be a matrix of order L by n, and C be a vector in the n-dimensional Euclidean space. Then exactly one of the following system has a solution. Has a solution, not both. System 1 is Ax less than equals to 0, Bx is equal to 0, C transpose x greater than 0 for some x in Rn, and system 2 is A transpose y plus B transpose z is equal to C y greater than equals to 0 for some y belonging to Rm and z belonging to RL. Here note that z is unrestricted in sign. Why z is unrestricted in sign? Because z is associated to this equality. This is a rule of thumb. If you have some equalities, then corresponding variable in the system 2 will be unrestricted in sign. However, if you have inequalities, then corresponding variable in the system 2 will be restricted to a non-negative quantity. Fine. Now, as a proof, let me write out the equivalent system corresponding to the system 2. System 2 is equivalent to, we note that we can write it in the following manner: A transpose Y plus B transpose Z, let me write it as Z1 minus Z2, and this is equals to C for some Y greater than equals to 0 and Z1 greater than equals to 0, Z2 greater than equals to 0. We note that any Z that is unrestricted can be written as difference of two non-negative quantities. For instance, if we try to write, let's suppose minus 5, then we note that we can write it as 3 minus 8. 3 and 8 both are non-negative quantities. For a positive quantity, if you want to find 5, then 5 also can be written as, let's suppose here, 8 minus 3. Both are non-negative quantities, right? So we know that any unrestricted in sign value, positive or negative, these can be written as difference of two non-negative quantities. Fine, z1 minus z2. These are vectors here, z1 and z2. Those are vectors. For some y greater than equals to 0, y is belonging to Rm, z1 is belonging to Rl, as well as z2 is belonging to Rl. Fine. Now this is sufficient hint. This will now be written as A transpose B transpose minus B transpose times the vector here is M plus L plus L dimension, Z1 Z2. Fine, this is equals to C. Now you treat this is your matrix A in the system, A dash say, in the system 2, and then it has transpose you consider, and this is your vector, let's suppose capital Y. Capital Y is belonging to R M plus L plus L, R M plus 2L, and all the components Y are greater than equals to 0, and therefore this is your system 2. System 2 in the Farkas lemma. Now try to write what is the corresponding system 1, and that will prove the corollary 3. With this, now I end of the class here, and on the next day I will try to consider to discuss the notion of convex functions. After defining the convex functions, we will try to have several examples, because convex functions, they do play very important role in optimization theory. The most important result in convex optimization is that if you are trying to optimize a convex function, then any local minimum is a global minimum, and any stationary point is also a global minimum. Fine. And not only that, last day I have mentioned, wherever you have a local minimum of the function, then the function must have a local convexity. Locally it will look like a bowl type or a bathtub type figure, and this bathtub like figure, bathtub like surface or a bowl type surface, they are nothing but the convex functions. Mathematically we'll define on the next day what do you mean by convex function, and then we will try to find several sorts of examples and also several characterizations of convex functions. How do we how do we check that a given function is a convex function? Those results are called as characterization results. In characterization result, we will have zero order condition, first order condition, second order condition. In zero order condition, we will not involve the derivative of the function. In the first order condition, we will involve the derivative of the function. The gradient will be involved. With the help of the gradient, we will try to find we will try to find a characterization of convexity of the function. In the second order characterization, with the help of the Hessian, we will try to find whether the given function is convex or not. So several characterization results with the help of epigraph or sublevel sets, we will try to find whether a given function is convex or not, or with the help of the gradient or with the help of the Hessian of a given matrix, we will try to find whether a given function is convex or not. These are the agenda in the next lecture. In the next lecture, we will try to discuss rigorously the idea of convex function. Fine. Thank you all for your kind presence.